sorry for that. So I would like to give an overview of the synthesis development of LSZ102 from a Suzuki coupling strategy to a CH activation. So the molecule, the structure is depicted here on this slide. It's a selective estrogen receptor degrader inhibitor, tricks cell into self-destruction of its own receptor, and the indication is breast cancer. The early phase synthesis was a long 10 linear step actually to the API starting material. It started from 3-methoxythiophenol. First step was this alkylation with bromoacetaldehyd diethyl acetal, then followed with the cyclization here to make the benzothiophenol ring. The thiophene was oxidized to the sulfone, then brominated here. We had a 4-bromophenol SNAR reaction. The bromo was reduced with sodium borohydride, and the sulfone was reduced by diol, and then we had a Heck coupling, palladium catalyzed, NBS bromination again, and then the ester hydrolysis. So there were several column chromatographic steps involved. We had several genotoxic and toxic reagents like BF3, etherate, metachloric perbenzoic acid, bromine, and with the 4-bromo phenol, we had a potential risk of bromodioxins because 4-bromophenol can also contain polybrominated phenols, and they could be the source of bromodioxins, which are highly toxic and have to be tested on very, very low level. So this triggered actually to, I mean, the later stage, the GMP steps then started here from this intermediate here, from the methoxy compound. There was the demethylation with BVR3 to the phenol, and then the Suzuki coupling with the sporonate. The crude drug substance-free acid could be isolated, actually crystalline as a dicyclohexylamine salt. We had two major impurities. The one was the desbromo coming from the Suzuki coupling, and the other one was here a vinylic impurity, just an HF elimination. They could be partially reduced by this dicyclohexylamine salt, but however, in the first GMP step synthesis, we had to do a column chromatography on the reversed phase. This was very tedious. And then the drug substance was isolated actually as the free acid just by pH first basification with sodium hydroxide, then it was in the water phase, and then just acidification with HCl. However, we still had residual TBME above the levels of tolerance, and also sodium chloride was incorporated. So it really needed then a better synthesis. The side chain here was made actually from this bromofluoride derivative by a Miura coupling with bisphenolate diboron, palladium catalyzed with palladium tetrakis with palladium bisphenol phosphine dichloride, and then this was purified also by column. The first improved early phase synthesis, actually we found out that we could actually recrystallize this dicyclohexylamine salt from methanol water. And this worked, so we could actually reduce these two critical impurities by quite a bit, and we could get rid of the column, the RP column chromatography. The isolation was still the same.
Markus, sorry, we couldn't see the chemical bonds actually. Can you present it here? Yeah, the present screen would be great. But the other screen can be sharing, because I think you have the multiple screen. We are seeing only the screen one or whatever it is. We could see the second screen.
Okay, so
because the chemical bonds were too small.
Yeah.
Here. Yeah, the first one, the first guy. If you see the taskbar, then the first one would be the one. Can you re-click this Alt tab again? Yep, yeah, the first one. Yep. No, now the second one actually.
Yeah, this one.
Yeah. Still might be the other screening might be. Okay, you can continue in the previous version. It's fine. You can click escape and you can click on the previous. Yeah. Yeah. Sorry.
Sorry for that. So I can make it a little bit bigger. Is it better now?
Yeah, you can just zoom. Yeah, now it's actually pretty perfect. Yeah. Thank you.
Yeah. Okay, sorry for that. So where have I been? So the first, then the second improved early phase synthesis. Actually, we made use of the Higa cyclization. We started from 4-methoxycinnamic acid with thionyl chloride as the reagent, and we could make this benzothiazine ring in one step, which was esterified. The acid chloride was not isolated, was directly esterified to the methyl ester in 47% in 2 steps, then hydrolyzed and decarboxylated, again oxidized and reacted with 4-bromophenol. And then we ended up in this intermediate 8, which was the first common intermediate to the first synthesis. And then we carried on. But when we were at this API starting material, we found out that we had a chlorine purity originating from the first step. And this was actually co-eluting with the main. We couldn't identify it in analytical column until this intermediate. And there we had to do 2 recrystallizations actually to remove it. So this was also not a very good thing. Then the final improved early phase synthesis made also use of this Higa cyclization. So we had the same chemistry here to make this ester, which was then decarboxylated. But then we oxidized only to the sulfoxide. The sulfoxide had the advantage that we don't have to reduce it later on with diabol. We can reduce it under much milder conditions with diethylphosphine TMS chloride. And this is then compatible here with the ester. So we could directly actually do the SNAR reaction with the 4-hydroxycinnamic acid methyl ester, avoiding any bromophenol. So the bromodioxine risk could be eliminated here. And then this product, which was isolated in 86% yield, could be then reduced to the benzothiazine ring, and which was not isolated. It was. Can you still see the screen?
No. We are seeing the similar ones as in the previous. That would be better if you just zoom it. No, you can just go back to the presentation and you can just zoom it. That would be better in this case.
So zoom. I mean, I can make it a bit bigger, yeah.
Yeah.
This is
Wrong presentation.
This is.
Yeah.
No.
Yeah.
Okay.
Or can you show the I sent you the slides, if you can present it from your side, is that possible?
Yeah, but now we can see it actually. Now we are
You
fine.
can see it, okay.
Yeah, we can see it. Yeah.
So sorry for that. And so the side chain as the final steps actually. So the Miura coupling went with bisphenol diborane and palladium bisphenylphosphine dichloride, potassium acetate in dioxane. So we could actually isolate this 17.8, which was then purified by low temperature crystallization from heptane. It has only a melting point of about 33 degrees. And the problem was also that this product exhibits a strong thermal decomposition energy. So the distillation, and we had several distillation processes in here, was actually difficult from a safety prospect, because the onset was sometimes shifted to lower temperature, and this exhibited big danger, especially in scale up actually. The synthesis of the starting material here, we also looked into that one. It started actually here from the bromofluorobenzoic acid. So first step, ethynyl chloride, we made the acid chloride. Then with diethyl malonate, magnesium chloride, triethylamine, we could make this beta diketoester, which was then hydrolyzed under acidic condition. And in the same pot, actually, decarboxylation to the acetophenone. And then with SO4HF chemistry, we did the difluoro compound 18 in pretty decent yield, actually, both steps. So the non-GMP part, the oxidation of the sulfoxide only to the sulfoxide was actually a benefit. So we could eliminate the 4-bromo dioxin risk, and also this 7-chloro impurity was under control after first process improvement in the first steps. But there was still challenges. So it's still a long linear sequence. The use of PBr3 on large scale. The Suzuki route uses this intermediate 70B, that's the boronate ester, which has a low melting point, exhibits a high thermal decomposition energy, and this triggered the need of an alternative synthesis for a final process. And we were still thinking about using this Higa cyclization, but actually instead of using the methoxy compound, we wanted to use the bromo. So we started off with the 4-bromocinamic acid and used the bromo as a masking group for the phenol. And this was actually, the strategy was working pretty good actually. So we did also here the first step, the cyclization, the Higa cyclization, and then transforming to the ester. Actually, the yield could slightly be improved to 55%. Here, the decarboxylation, we changed the solvent from DMSO because DMSO under with hydroxide is also thermal risk, also described in several literature. And so we changed that to NBP, N-butylpyrrolidone. It was working also well, oxidation to the sulfoxide, and then again the SNAR, followed by the reduction of the sulfoxide, yielded finally this bromo acid. And there we found, actually this is chemistry from Buchwald, with a palladium catalyst, allyl palladium chloride dimer, and tertiary-butyl-6-phos with potassium hydroxide. We could transform the bromo aryl to the phenol. This was working then pretty fine in 85% yield. And then we could still carry on actually with NBS bromination here on this step, this stage to in 87%, and then do our Suzuki coupling with this intermediate, which is still the risk. But in parallel, we were also investigating actually to do the CH activation here with the precursor of this 17B, the bromo fluoro aromatic with palladium acetate and cyclohexyl diphenylphosphine, then giving this the same intermediate actually what we wanted also to isolate as the dicyclohexyl salt, and then purify. So the first key step was this palladium catalyzed conversion of the aryl bromide to the phenol. This was working pretty well. Actually, with we added tetrabutyl ammonium bromide as a phase transfer catalyst. We found that actually it is better to only add at the beginning 3 equivalents of potassium hydroxide, and after about 3 hours at 60 to 65 degrees, we had about the conversion of 70%. This was checked by IPC, HPLC conversion IPC. Then another 1 equivalent potassium hydroxide was added, and the stirring was continued overnight at 60 to 65 degrees. And then we had full conversion. The isolation was done actually from 2-methyl THF heptane by crystallization. And there was also we had a chloro impurity here on this position, also a chloro instead of the bromo. This was also originating from the Higa cyclization, but this also converted to the desired product. So that was not an issue actually. So the manufacturing followed the analogous route. The key was the very good inertization. That was very important, and we could actually perform this on 85 kilogram scale and 100 kilogram scale, and in both campaigns the yield was about 85%. Actually, after the campaign, we found that tetrabutylumonium bromide as the phase transfer catalyst is probably not necessary. The isolated yield I already told is 85 or 86%, with purity of greater 98%. In order to deplete the residual palladium, we added sodium diethyl carbonate. However, there was a slight danger of CS2 formation after acidification of the aqueous phase. However, with measures in the pilot plant, we could control that. But for future campaigns, definitely this solution has to be found. The next step, the key step, is CH activation. So we started here also from this phenol here, everything unprotected. The carboxylic acid and phenol were not protected. And here is bromoaromatic. There was an extensive catalyst screening ongoing. And finally, we found the palladium acetate and cyclohexyl diphenylphosphine. By using sodium tertiary butoxide, 5 equivalents, THF solution, works pretty well, actually. So the palladium catalyst had to be preformed. Palladium acetate and the ligand were mixed in THF. And then the other 2 starting materials were also mixed in THF. Sodium tertiary butoxide, the base in THF was added, and the reaction was heated to 65 and stirred for at least 14 hours. Usually we had a conversion of greater 98%. So, the reaction we found, this is very water sensitive and oxygen sensitive. So this was critical for the reaction to avoid any moisture. After complete reaction, the THF was partially distilled off. We had again treatment, palladium removal with N-diethyl carbonate. And so the product 15A, that's the dicyclohexylamine salt here, was then isolated as a wet product, usually with around 97% purity. We dissolved that in sodium hydroxide, removed the dicyclohexylamine with heptane extractions, and then the mono salt of the LSZ102, so where the carboxylic acid is still the sodium salt. However, the phenol is protonated. This was the ideal pH was at 7.8. We could actually isolate this step, the monosodium salt, and this gave a very good purification power in a yield of about 70 to 75% over these 2 steps. So the CH activation, dicyclohexylamine formation, and salt release, salt splitting, and then isolation as the monosodium salt. We got about 70 to 75% yield with an assay of about 85%, and the purity was usually over 99%, and the palladium levels were down to 5 ppm. We had 3 batches executed on 40 to 50 kilo scale. One critical thing is actually is reported by these people from Johnson Matthey, actually, that palladium acetate, the quality of palladium acetate might be very critical, and we found that as well. So palladium acetate, we finally measured the NMR of the palladium acetate. So this was a batch in the NMR in CDCl3 in deuterochloroform and NMR. So you see a lot of signals of the acetyl group. So this palladium acetate was not suitable and didn't give any good results. Whereas this palladium acetate batch, where you see a predominantly 1 signal for the acetyl group of the palladium acetate, this showed a good catalytic activity and was a good choice for this CH activation step. So this monosodium salt was filtered actually very badly in the pilot plant, and we had another additional palladium removal with N-acetylcysteine to the crystallization solution, and then we found actually that in one of the batches we had a byproduct. Actually, it was increasing the desbromo byproduct, and we didn't know why. But then we looked at the UV spectra and saw that this is not the same UV spectra. We also made HRLCMS, and we found this compound here that could isolate and elucidate the structure. And it was definitely clear that probably the N-acetyl cysteine wasn't washed out prior to the drying efficiently, and did this Michael addition to the LS but it was still under uncritical level. But however, in the next batches, we avoided this N-acetyl treatment in the recrystallization step actually, and then this problem could be solved. We found several impurities in this step, but they could all be removed to uncritical levels, especially during these two crystallizations of the dicyclohexylamine salt and the monosodium salt. So they were all under control and were below 0.2 or 0.1% area percent in HPLC. The final isolation strategy of the API. So we started here from the monosodium salt of the drug substance. Then with phosphoric acid, it was acidified to the free acid and extracted with ethyl acetate. And then the ethyl acetate solution was actually then isolated by a spray drying. However, the yield of the spray drying was very bad. It was got some kind of a plasticization of the product in the cyclone. So there was a big yield loss in this isolation after the spray drying. So then obviously new isolation strategies were carried out by our crystallization experts. And then they found actually that the LS can be crystallized with as a co-crystal with a beta in here is the structure here. And also they found a crystalline free acid, a form they managed actually to crystallize the free acid. And also we found that actually in the CH activation, it seems not to be necessary to preform the catalyst, the ligand diphenyl cyclohexyl phosphine and palladium acetate can be added to the mixture of the two starting materials. So this was actually performed in the next scale-up batch. And then what we did after the dicyclohexylamine isolation, we still liberated the free base, and then instead of isolation of the monosodium salt, which had a bad filtration ability, we co-crystallized this with as a beta-in, and this also gave a very good purification power. And then the goal was actually then to crystallize as the free acid just in acetic acid water. Beta-in goes into the mother liquor, and this worked actually on kilo scale pretty well. So these were the results of the several batches we had. So we had them on around 50 kilo scale. Palladium was well under control, below 5 ppm. The purity was above 99%. And the dicyclohexylamine, which is Ames positive, and the genotox, which has to be controlled, was also below 5 ppm, which was in accordance to the ICH guideline. We then focused again on the early steps, actually. And we thought, I mean, what we are actually doing in the early step synthesis was actually here decarboxylation and then activation of the aromatic ring as a sulfoxide for an SNAR to make this nucleophilic aromatic substitution. We thought, why not making use of the ester? Actually, this is probably not so active than the sulfoxide. But however, we tried, we actually wanted to make the tertiary butyl ester, but that was not stable. But finally, as the ethyl ester under strictly anhydrous condition, using potassium carbonate and butyl tertiary butyl ammonium bromide in DMSO at elevated temperature, one could actually make this SNAR using the ester as an activation group, electron withdrawing group. I mean, there were other byproducts formed, but still that was possible. And then finally, after ester hydrolysis, these two esters, they were already partly hydrolyzed in this step. After complete hydrolysis, we were able in potassium acetate or potassium carbonate in DMSO, potassium acetate is preferred under thermal condition to decarboxylate the product. And then we were at the same intermediate for the bromo to phenol exchange. This was done on kilo scale. Actually, the overall yield until this step here was about 20 to 25%. On the old route, it was 28%. However, the old route using this sulfoxide, we had to use hydrogen peroxide and trifluoroacetic acid to make the sulfoxide in dichloromethane, and then for the afterwards the reduction of the sulfoxide, we used triphenylphosphine, producing triphenylphosphine oxide. So these two HSE unfriendly steps could be removed. I mean, further process development obviously will be necessary actually to further improve this new process. So finally, our proposed final synthesis would start here from 4-bromo cinnamic acid. In this first step, the Higa cyclization, we make the ethyl ester. This is a 54% yield. Then potassium carbonate, DMSO, toluene at 70 to 80 degrees makes this SNAR reaction. And then after hydrolysis, this is isolated as a dicarboxylic acid in 57% yield, decarboxylation to get this intermediate, then conversion of the bromo to the hydroxy with this palladium catalyst, and then finally the CH activation step here, the coupling with the bromo aromatic, isolation as the betaine, and then crystallization of the API as the free acid, removing the betaine, and maybe a final API recrystallization step. So in a nutshell, the project achievements in 4 years. So we started actually the synthesis from 10 non-GMP steps and 8 GMP steps for the phase 1 to an overall 7-step proposed final synthesis. We could avoid critical steps, reagents such as BBR3 for bromophenol with the risk of dioxin, the handling of this boronate, which has a low temperature crystallization, thermal safety issues. We had 6 different syntheses in 7 different campaigns, and the first implementation in our development actually of a CH activation on 50 kilogram scale. And the catalyst going from an air-sensitive tetracrystalphosphine palladium to a stable palladium acetate and ligand, this made things easier. And the drug substance actually could be isolated from amorphous to crystalline, and that work was actually published in OPRE in 2020. I would like to thank, there was a big team involved all over the company and also with externals. I would like to thank all the team members for their input and for their really hard work they did, also the external partners and the internal partners within Novartis, from research to production to analytics. And I want to thank you for your kind attention.